Philip Scharf. He is an astrobiologist. He's someone that I've been following his work for many, many years with great admiration as a scientist and also as a public writer. He is a serious and very compelling writer and advocate of public understanding of science. So he was born and educated in England. He received his PhD, his bachelor's degree in physics from Durham, and his PhD in astronomy from the University of Cambridge. And then he did a postdoc and an X-ray astronomy and observational cosmology at the Goddard Space Flight Center and Space Telescope Science Institute in Maryland. And then he was also a research scientist at Columbia University in New York. And now he is the director of the multidisciplinary Columbia Astrobiology Center. And I'm very jealous. I wish we had one at Dartmouth. Seriously, we should. Anyway, his research interests include the study of exoplanets, exomoons, and the nature of environments suitable for life, which he's going to talk to us about today. But first, let me just do a little advertising. He has written at least 4 books, as far as I know. One of them is called Extrasolar Planets and Astrobiology. The other one is called Gravity's Engines: How Bubble-Blowing Black Holes Rule Galaxies, Stars, and Life in the Cosmos. The Copernicus Complex: Our Cosmic Significance in a Universe of Planets and Probabilities, so a very important question. And The Zoomable Universe: An Epic Tour Through Cosmic Scale from Almost Everything to Nearly Nothing. I love it. And so today, Caleb is going to talk to us about, well, the title is As Worlds Turn. As you can see already, things are turning on the screen there. And that's it. You know, let's see what he has to tell us about. Thank you, Caleb, for joining us, and welcome.
Thank you so much, Marcelo. Thank you for the beautiful bit of advertising for various books. I have a new one coming this summer as well.
Oh, well, we'll make sure we review it for sure. So, folks, just one thing before Caleb starts. If you have any questions, try to use the Q&A or raise your hands, and we'll do our best to reply, to have Caleb reply. All right, thank you.
Okay, thank you. And thank you so much for inviting me to do this. Obviously, by the end of the week, we're probably all a little bit exhausted from Zoom calls. And what I've learned, as I'm sure you've learned, is that actually the rate of information exchange on Zoom calls somehow drops away. Giving classes on Zoom calls is much less efficient. So I've tried to pare down my material a lot to eliminate a lot of sort of technical details, really get the story across to you, and hopefully it will make sense and be of interest to you. So I thought I would talk about something quite fundamental that has come up in our quest to understand planets under the stars, exoplanets, and in particular to begin to scope out the sorts of environments that might be out there in the universe that could conceivably harbor life. And if I just move to the next slide, I think this sort of helps begin that story. So if this movie is playing for you across Zoom, you see a beautiful night sky, Milky Way in it, moving through the sky, and the sun is about to rise. And one might ask, well, what is special about this view? Of course, it's a beautiful view. It's time lapse of our night sky. You can see the stars and our galaxy, and then the sun coming up and so on. But what is really special about this view is that it changes. And that changes, of course, because we live on a planet that is spinning. We live on a rotating world. And that fact is quite interesting. And even though it's so basic, so fundamental, that we perhaps don't even really think about it terribly much, it has profound implications for the nature of the environment that exists on Earth, and by extension, that property of a planet that's spin will have things to tell us about the potential environment on other worlds that maybe spin differently than ours. So to plunge right in here, one thing we understand from our current picture of planet formation, which is still very much in its infancy, and the gaps are being filled in between theory and reality as we gather more and more data on exoplanets and on protoplanetary systems and so on. One thing does seem clear is that for worlds like the Earth, so what I will call a rocky planet, the initial spin rate of these worlds, the day length of these rocky worlds, will have a very wide range of values. It seems like a very stochastic process, a lot of random things that go into setting the initial conditions for a rocky world like the Earth. And so our day length, it may be on the short end of things, it could be on the long end of things. We don't really know. All possibilities are there. What we do think we understand is that the spin or rotation of a rocky planet is likely to change over time. And part of that is for reasons that we're quite familiar with, things like stellar and satellite tides. So on the Earth, tidal interaction, both with the sun and the moon, has played a big role in gradually evolving the day length of the planet. And I'll come to this in more detail in a couple of slides, more quantitative detail. The Earth today is, we think, spinning quite a bit slower than it was a few billion years ago, largely due to those tidal interactions. But there are other things that could play a role in maybe not our own solar system, but certainly in other planetary systems, to do with spin-orbit resonances. Collisions, of course, may reset or alter the planetary spin. Things like atmospheric friction may play a role. The atmosphere and solid surface of a planet, they're very strongly coupled, but that also means that an atmosphere can alter the solid body rotation of a planet. So our expectations for planetary spin are broad, but we do believe that there will be evolution. As I'll talk about, that evolution in planetary spin is already suspected to be important for assessing the possibility of some of these rocky worlds resembling the Earth in some way, or at least being, I use the term habitable in the broadest sort of astrophysical sense, that there may be a possibility of temperate conditions conducive to sort of complex chemistry that exists here on Earth and that has played part in giving rise to life on Earth. The caveat to all of this is that we know that doing something like actually measuring the day length of an Earth-like world or an Earth analog world around another star is going to be enormously challenging. It's very difficult for even larger planets to imagine how to do this, various astronomical techniques we might employ. For small planets, it's something that feels like it could be a long, long way into the future, even with upcoming telescopes, James Webb Space Telescope, things like LUVOIR and HabEx, and all these plans for larger and larger telescopes. But for that reason, I think it's important to understand what spin does for us. How does spin matter in evaluating planets? Because if it's really important, then actually that challenge of observationally pinning it down is worth pursuing. So let me talk a little bit more about all of this. I'm going to split my discussion into two parts. One is quite conventional, and it will be talking about the influence that planetary spin has on planetary climate and potentially on, therefore, on life. Part two, I like to throw something a little more outrageous in there, usually when I'm talking. It will sort of flip that on its head, and I'll make an argument or proposal for a way in which life on a planet could actually influence planetary spin. This is not talking about technology or anything like that. This is something that could conceivably happen just because of biological evolution on a planet. So I put yes really in parentheses there to emphasize that, yeah, it's a little wild, but it's Friday afternoon, so let's go crazy. Let me begin with a review. Many of you may not have thought about this for a very long time. You probably encountered some of this perhaps in your high school physics or later on. But let me just review and remind us of a basic understanding of how something like planetary spin should change with time. And the main concern is to do with stellar tides, tidal forces, gravitational tidal forces. And obviously for the Earth, we have the moon to complicate things, but I'll ignore that for now. So in this little cartoon, we're looking down onto the pole of a planet. It's spinning in the anti-clockwise sense, following that little red arrow, and its orbit is in sense indicated by the arrow at the bottom of the screen. So in this situation, as we recall, and actually Richard Feynman gives a beautiful explanation of this. If you really want a good explanation, you can go back and look at some of his writings. This planet experiences differential gravitational forces across its radii because of the different distances of those parts of the planet from, in this case, the star, which is over on the left-hand side. So in a very exaggerated form, hugely exaggerated form, there is tidal distortion of the figure of the planet. Okay? So this is an enormously exaggerated version of that. The planet will be distorted towards an ellipsoidal type shape. It's not perfectly symmetric, but that doesn't really matter for the argument here. And you might imagine that that distortion should be pointed directly at the star. So it should be pointed towards what we call the substellar point, which is the closest point of the planet to the star. And it would be, were it not for the fact that the planet is spinning and that there is a response time of the material composition of the planet, the ocean, the crust, and so on. And so what happens in effect, and this is what happens with the Earth, both with its response to the moon and to the sun, is that the spin constantly carries that ellipsoidal shape out of alignment with the direction of the star. And so what is presented to the star is always askew. So the peak of that distortion always lies away from the substellar point. Consequently, this asymmetry means that the regular gravitational attraction to the star can exert a torque on the planet. Okay, so that torque acts to slow down the spin. It acts in the opposite sense to the spin. And in the case of the Earth, both the solar tides and the lunar tides are acting in that sense to gradually slow the Earth's spin down, increase our day length. And of course, the interaction with the moon is a little more complex. The moon is moving away from us as this happens and so on because of angular momentum exchange and energy loss and so on. But this is the basic scenario. And a little more mathematically, we can, to first order, because computing the nature of these tides is actually enormously cumbersome. And it's still not really agreed upon what the best analytic approach or semi-analytic approach is. This is work that goes back a long way. In fact, one of Darwin's descendants wrote an enormous tome on this back in the late 1800s, early 1900s, that digs into questions of tides and so on. But the essential parts are in this mathematical expression up here. So this d omega dt is the rate of change in the angular frequency of the rotation. And as it's written here, it's a negative change, so it's a deceleration of the spin. It depends on the stellar mass, M star. It depends on the size and the mass of the planet. Depends on this quantity Q that I'll talk about in a moment. And importantly, it has a very strong dependency on the separation of the planet and the star. So this R in this expression is essentially the distance between the star and the planet. So it's a 1 over R to the 6th dependency. So it's very strongly dependent on that. And that's very relevant for when we're thinking about systems other than our own solar system. For example, exoplanets around lower mass stars, where the range of orbits that those planets might be temperate and habitable places them that much closer to the star because the star is that much fainter than our sun. But that also means that there are exaggerated tidal effects compared to our situation for the Earth. And so the spin down rate of potentially habitable planets around lower mass stars is expected on average to be significantly higher than it is in our solar system. This little graph is, there's really nothing much to say about this. It's just a reminder of this form of those curves. So it's the rotation period versus time. It's taken from a beautiful review by Barnes in 2016. And these curves just remind us of the form of this deceleration of spin, this change of spin, and that planets at some point may reach synchronicity. And I'll say what that is in a moment. Just one technical aside, this quantity Q is a tidal dissipation factor. So all of the messy physics that we really don't understand gets shoved into this single parameter. And it essentially represents the energy loss per revolution, or per, per revolution of the planet due to tidal distortions and tidal torques. So we can look for the value of Q by using things in our own solar system, the moons of Jupiter, our own moon, and so on, to try to pin that down. But it's a very poorly known parameter. And for the Earth, it has likely changed over time. So I'm not going to go further into thinking about Q, but just to remind us that there are many uncertain parameters in a lot of what I'm talking about, although we have some idea of their general range. So everything I will say subsequently sort of fits into that, but it's a big target to hit. So it's an easy target to hit. Statement I have at the bottom here is important. So if we look across the range of potential rocky planets around other stars, and particularly stars that are lower mass, as I mentioned, what we find is that overall, you can have rocky planets that are potentially habitable, temperate, experiencing a wide range in spin down rates. They can spin down to a synchronous state, that is often also called a tidally locked state. So our moon is a tidally locked object to the Earth. So we only see the one side of the moon. Tidal lock means basically a permanent day side and a permanent night side to a planet, or something close to that. You can have pseudo-synchronous locking states as well. But that time scale is anywhere from about 1 million years to 10 billion years. And it depends acutely on the precise configuration, and in particular what mass star we're talking about. If we're just interested in planets that might be temperate, might have the right amount of stellar input to have some moderate temperatures. So this is interesting. It means that many of the exoplanets that we're interested in, looking for perhaps signs of life, may have been in situations where their spin down rate is much, much faster than for the Earth. So some may have spun down to a tidally locked state, but we're also likely to have planets in all the intermediate states as well. So there's a wide range of possibilities for day length on planets. Okay. So that's really just setting the scene for what I really want to talk about, which is to do with climate and to do with the relationship of spin or day length to the actual surface conditions on a planet. Now, we've long anticipated that spin has all sorts of profound effects on the planet's climate dynamics, but we haven't really explored it that much over the last century, really. In a very naive sense, spin or rotation is going to affect common assumptions about insulation, the amount of light, the amount of energy being absorbed by the planet from its star, its albedo, its reflectivity, and its thermal emission. We tend to work in a so-called fast spin approximation. But if a planet is spinning very slowly, and one side of the planet, for example, is darker than the other, that has profound implications for the absorption or reflection of light, especially if the planet is spinning slowly enough that things like thermal inertia timescales are similar. So you may have sort of weird seasonality of slow spinning planets, even though they have no axial tilt and their orbit is perfectly circular. So there's some interesting things that come up there. But perhaps the biggest factor is to do with atmospheric circulation. To some extent, oceanic circulation, if that is included in this. And for quite a while, people have thought about this, but not in great detail. And I'll explain in my next slide. Part of the reason is we haven't been motivated to think about this in particularly great detail, because we're focused often in climate studies on the Earth. Spin will alter atmospheric circulation. So this is kind of, on the face of it, basic physics. You change the angular momentum of a system, you will change things like the large-scale circulation patterns of an atmosphere. So a couple of cartoonish illustrations of this at the bottom here, just to get you thinking about it. If we look at the modern Earth, very exaggerated form, the atmosphere on the large scales, large S scales that we look at for the Earth, is divided into these massive circulation cells. So for example, around the Earth's equator, both sides of the equator are these things called Hadley cells. This is where warm air rises from the equator. Then as it cools, it falls away to higher latitudes. But it is, of course, carrying more angular momentum than these higher latitudes. So this is basically the Coriolis effect is at play. So as that air cools and falls again, it can generate interfaces or instabilities between it and the next latitude bin. You get things like jet streams forming between these cells. Jet streams help separate out these cells. Of course, right now, certainly in New York, I'm sitting here, it's snowing outside, we're feeling the effects of variations in the jet stream separating the polar region of our atmosphere from the intermediate region that we usually inhabit. So these are like donut shells of donuts, bands of circulation wrapping around our planet. And they complicate the movement of thermal energy around the planet. So I'll say more about in the next slide. This is really just to get us thinking about the basic physics. We expect and think that for slower spinning planets, the structure of these major circulation cells will change. So for example, a much more slowly spinning planet, it's possible that these cells will extend all the way from an equatorial region up to a polar region. And that's really because there's less angular momentum in the system. That's reason to sort of mess this up. An extreme example of a faster spinning planet would be something like Jupiter, which has many, many of these bands, many jet streams, many cells rotating in this way. So we have had a kind of general sense of how this might change, how circulation patterns and energy transport might change as day length of a planet changes, but we haven't really investigated it in detail. In very crude terms, so for example, you can model the energy transport as a function of latitude on a planet in terms of like diffusion approximation. Diffusion approximation tells you that the efficiency of energy transport will scale like 1 over the angular frequency squared. And so another way to think about this is faster spinning planets will have more of those circulation cells that have more jet streams. It becomes harder for input energy at the equator, for instance, to make it further up in latitude towards the polar regions. It's literally blocked by these rotating, circulating atmospheric patterns. So we would expect slower rotating rocky planets to have less extreme equator to pole temperatures because the equator can't shed as much thermal energy towards higher latitudes. It's prevented that diffusion of energy is slowed down. I'm sorry, is sped up in slower rotating planets, but slowed down in faster rotating planets that block the movement of hot air basically to higher latitudes. So we have these general expectations, but the solar system really doesn't give us very much to work with. We really have the rocky planets with atmosphere. We've got Venus, we've got Earth, we've got Mars, and we'll include Titan in the mix. But it turns out the angular frequency for all of these planets is not so very different from each other. Venus is rather slower, but overall it's only 2 or 3 orders of magnitude range, which is not a great deal. So that gets us to a project that I'll now explain in a little bit of detail, where we've applied a very sophisticated climate model, so-called general circulation model with GCM, to this basic question: what happens as planetary spin changes? So I have to do a little advertising here. So, this work has made use of a new tool called Rocky 3D. It's an exoplanetary climate model. It was mainly developed by people at the Goddard Institute for Space Studies here in New York. It's a NASA laboratory here in New York associated with Columbia University. Michael Way has played a central role in driving this, along with a scientist called Anthony Del Genio. And the idea has been to take NASA's state-of-the-art Earth climate model and adapt it so that it can be applied to questions of planets that are not in an Earth configuration. That may sound kind of trivial, but actually it's an enormous challenge, an enormous task, because climate models built to understand Earth are very focused on the modern Earth, or Earth in a few decades or a few hundred years, and anthropogenic climate change and so on. Those models are highly tuned to be very good at solving that problem, making those models of a modern Earth. So it has taken upwards of 10 years, I would say, to get to the point where this climate model that we now call Rocky 3D has been adapted sufficiently that we can ask questions in a very flexible way. So we can literally think of an exoplanet or even an imaginary planet in some configuration created in the simulation. Simulations typically run on a supercomputer, and analyze the output. So this GCM, it models a full atmosphere, so it follows atmosphere as a fluid. It models an ocean, a dynamic ocean, so the ocean is also modeled properly using fluid dynamics. Includes chemistry, there are radiation schemes for radiative transfer. It can actually generate fake spectra, the sorts of things we might look at with future space telescopes like LUVOIR or HabEx and so on. So that's a very useful characteristic. And it has all sorts of physics built in. So just to give you an example, there are 3 kinds of snow that this model can generate and deposit on the surface. If we use the Earth template of topography, then we actually have river systems and lakes. We can model where precipitation goes on the planet, which is also very interesting. I won't talk about that today, but it's something we've actually played around with. So it's a good model. It is a model, so it has its incompletenesses, but it lets us really get into some of the interesting questions about what happens with potential exoplanets. So let me show you the results of a set of experiments. This was a couple of years ago that we started doing this. It took a while to generate the outputs of these supercomputer models. And it directly addresses some of these questions about spin and climate. What does planetary spin do for planetary climate? And we haven't really asked these questions before. We haven't been able to ask these questions in such a direct way. So the technical details here are not so important, but essentially we used a template that is the Earth, but we removed its axial tilt to simplify the problem. So it's a season-free planet. It has a slightly different atmospheric composition than modern Earth. Again, that doesn't actually impact anything I will show you subsequently. What we did was we modeled this planet at 1 astronomical unit from a star. That star has a solar luminosity, and then we bumped it up by 10% and 20%. So essentially 3 levels of stellar input to this planet. And then we ran over a number of rotation periods. So 1 times means 24 hours, 2 times means 48-hour day length, and so on, all the way up to 256 times the length of our present Earth day, 256 times 24 hours. So we don't model a tidally locked planet because that introduces some other complications. But we look at everything in between, what the Earth is doing today and what a almost tidally locked, synchronously spinning planet would do. A graduate student, Tiffany Jansen here at Columbia, she's actually just going to be graduating on from a PhD sometime later this year, fantastic student, did basically all the work here. So I'm just reporting the results that she got out of this. It's a big challenge doing this, both running the models and then analyzing the output. The models are complex, the outputs are complex, but one can extract some fairly straightforward seeming characterizations of these planets. So let me jump right away to some of that output. So the very first thing we did, it's a simple thought experiment. What happens if you take a planet and you look at it as it slows down in its rotation? What does that do to things like its temperature, for instance? So this plot shows the mean global surface temperature for each of our simulated planets. So each dot on this plot represents an entire simulation. So the mean global surface temperature as a function of rotation period for the 3 levels of stellar input. So the solar input 10% more and 20% more. And when we first saw this plot, well, certainly when I first saw this plot, confused. Well, what's going on? Planets seem to be getting cooler as they spin slower. Now, this is the mean global surface temperature. Okay, so it's evaluated by taking temperature measurements across the entire surface of the planet. But if you just take one of these curves, the input energy is the same. Right? The energy hitting the top of the atmosphere of each of these planets is the same, but just by allowing the planet to spin slower and slower, you can cool it down, which is not intuitive. I think the intuition is energy conservation, so the same amount of energy going in. So maybe you change some of the details of where things are hot and cold, but how can you change the global mean temperature of the planet? So that was the first puzzle we had to then try to understand. And I'll show you the next piece of the puzzle, which is closely related. So the mean global surface temperature is a useful enough thing to gauge what's going on with the planet, but it's kind of simplistic. A slightly improved measure that gives you a little more leverage over what's happening on the planet is what I call the fractional habitability. So that is the fraction of the surface area of the planet that remains between two temperature limits. In this case, temperature limits of the freezing and boiling point of water, so 0 to 100 degrees Celsius. So that's something we often associate with this idea of habitability, the possibility of liquid water on the surface of the planet. So what we can do is ask, on average, over an orbit, what fraction of the planet remains between those two temperature regimes? And that is what we've done here. Similar sort of plot, fractional habitability on the y-axis versus rotation period on the x-axis. Three curves for the three stellar input levels. And the interesting thing is, so you see it the most strikingly perhaps in the lower blue curve here, which is for a input equivalent to that of our sun, a modern sun, is that the fractional habitability of the planet peaks at intermediate rotation rates. And you could sort of make an argument that I think it also kind of peaks at these other input levels. It clearly drops off beyond that. So the fraction of the planet that is habitable or between these two temperature limits definitely declines as you move to slower and slower rotation. So this actually is very intriguing. It almost suggests a sort of Goldilocks zone, not in planetary orbit, which is how we usually think about habitable zones around stars, but actually in rotation rate or in day length. And it's somewhere around 16 days in this particular model, that is a more optimal temperature in terms of making sure more of the planet's surface area is temperate, which is intriguing and interesting. So the question is, why is this happening? What's going on? What's the underlying cause of this? So very briefly, I'll summarize that. I think there are three things that we were able to tease out of our simulations that helps explain what was going on. And the first we can sort of see if we look at the temperature maps. So each of these maps represents different day lengths. So we start at one time, so Earth day length, and slower, going slower and slower down to the bottom right-hand corner of this plot. It's pretty apparent that the surface temperature, for one thing, evens out quite noticeably as you track through these different maps. So for example, by the time we get to a 16 times Earth day length down the lower left-hand side, the temperature variations across the planet really have smoothed out. And that's a good thing because it agrees with what I talked about earlier, this expectation. As you slow the spin of a planet down, it's easier for thermal energy to be transported from equator to pole. Therefore, it's easier for energy to be redistributed across the planetary surface. And we think that is exactly what we're seeing here. At least in part, that is what's going on. So that's the first factor that comes into this. And if you're spreading thermal energy out more, it sort of stands to reason you're going to lower the equatorial temperature and perhaps raise the polar temperature a bit. So there's a possibility of overall lowering the global temperature, but it's not the full explanation. If we look at the very last plot on the lower right-hand side, you can see that continents are starting to become very cold. And that actually is an interesting clue as to what's going on next. Let me move to the other two reasons that we think we're seeing these behaviors of global mean temperature and fractional habitability. The first of these is, as you slow a planet down, it spends more time with one side of it being illuminated by the star and the other side in night, right, facing the outer universe. And during the night is a period where the planet is simply emitting thermal energy out to the cosmos once it filters through the atmosphere and clouds and so on. And if a planet is spinning slow enough, the nights become very long. And if that length of time becomes comparable to the thermal inertia in a system, then you can actually really cool off at night, so much so that you begin to draw down the global temperature altogether, which is kind of interesting. You also, and this gets a little more complicated, so I won't dive too far into it, you begin to see at very slow rotations a transition from the sort of atmospheric flow patterns that I showed you, so circulating with the angular momentum of the planet, forming cells around the planet and so on, to something that's more like a day-night circulation pattern. Or rather, the primary circulation is no longer driven by angular momentum, it's driven by day-night temperature and pressure differences. And so that may help explain this Goldilocks peak, because that Goldilocks peak happens a little bit before this kind of transition. So maybe that as you make that transition, nighttime becomes more important, day-night circulation becomes more important. That's where you now begin to dive down and actually reduce the fractional habitability of the planet. The last factor, which was really unexpected, came out of the fact that this model is so thorough and complete, even though it's still just a model. And that is, we noticed in this artist's diagram, this artist's representation, I'll come to the question in a moment, it's just a representation of this, that we found that actually what happens at very slow rotation rates, you get a persistent cloud cap forming on the so-called substellar point, the side of the planet pointing at the star. That cloud cap is highly reflective because it's cloud, it has a high albedo, and it actually acts like an umbrella. It actually depresses the temperature of the planet. So it only happens because you have something like water vapor in the atmosphere. So you need a condensable species in the atmosphere to form these cloudlets. It was very surprising, and it turned out when we dug around that a few other groups with slightly different models and looking at kind of different planetary configurations had also seen hints of this. So it is actually a prediction that we can make now when we're looking at exoplanets, that there may be these persistent cloud caps for the slowest rotating rocky planets with condensable species in their atmosphere. And that is really lovely because it's potentially a testable phenomenon for exoplanets. A cloud cap like this will present albedo changes. It could be seen in phase curve photometry. It can also be something seen in transit data because clouds are relatively opaque through transmission of light through an atmosphere. So it's a question, shouldn't be a strong correlation between planetary spin and orbital distance from the star? In other words, Goldilocks zone for optimal spin, planets close to its perigee. Yeah, absolutely. Not because of the initial states of the spins, but because of tidal evolution. So I think that may well be what you're getting at with that question. So yes and no. I think, I'll have to think about that a little bit. One runs into issues when you get to very slowly rotating planets, when that rotation rate begins to be similar to the period of the orbit, then you have to be very careful thinking about atmospheric circulation and illumination and so on. So I think my rough answer to that, and we can come back to it at the end, is yeah, there probably is a correlation, if I understand you correctly. So that's an interesting point. Maybe we can come back to that. Okay. So I want to jump to the last bit here, so as not to prolong things. See, I've already gone through most of my time. We've got 10 or 15 minutes left. I know these Zoom calls are very inefficient, but I want to, so given all of that, hopefully that just gives you a taster of some of the work we've been doing and some of what we can now deduce about the impact of things like planetary spin on climate. I'm going to ask an outrageous question. Can I flip this around? Can there be something about life that reaches back and influences the evolution of planetary spin? So how does this work? Well, I'll go back to this picture. It's very similar to the picture I showed at the outset. So it's the same depiction of a stellar tide, distortion of a planet. I've drawn it slightly differently here, but it's the same basic thing. The spin of the planet carries the peak tidal distortion away from the substellar point, so a torque can act on the planet to slow it down. But it turns out there's another kind of tidal effect one has to think about, and it's called a thermal tide. And so thermal tide, and this was something actually Kelvin first thought about, he called it his thermodynamical acceleration. Thermal tide is if you have a planet like the Earth and it's being heated during the daytime, at the substellar point of sort of maximal stellar input, energy is coming in, the atmosphere gets warmer and warmer. Now, warm atmosphere has different pressure and density than cool atmosphere. And what happens is that that heated spot essentially pushes atmosphere away from itself, pushes mass of the atmosphere away from itself to either side of the planet, away from, if you will, the hot spot on the planet. There is a redistribution, a daily redistribution of the mass of a planetary atmosphere because of that thermal input. What is interesting about that is just like with the stellar tide, if the planet is spinning, you can have a situation, and I've drawn it here in sort of murky brown orange colors, my representation of the redistribution of mass in the atmosphere because of the thermal input. You can have a situation where because of the spin of the planet, again, you get an asymmetry what's presented to the star, and therefore there's a possibility of the gravitational pull of the star imposing a torque on that distorted atmospheric mass. And that, depending on the details about the spin rate of the planet and the atmosphere itself, that torque can quite easily act in the opposite sense to the usual gravitational torque, the stellar tidal torque that spins a planet down. So it can actually act in the opposite sense, try to speed things up. Now, that's the atmosphere. So does that really matter for the solid body of the planet? Well, atmosphere and surface are usually very well coupled in rocky planets. There's an atmospheric boundary layer, angular momentum can be transferred through from the orbit through to the torque, from the torque on the atmospheric redistribution. So absolutely yes, there can be a transfer of the torque on this modified shape of the atmosphere all the way down to the solid body motion of the planet, the solid body spin of the planet. But not surprisingly for the Earth, with a thin atmosphere, the effect is typically very, very small. So why bring this up? Well, it actually, I'll put this note up as well. When Kelvin was thinking about this in the late 1800s, he actually thought that the effect could be quite strong. And the reason for that was that he recognized that a resonant state can exist. That resonant state can exist between the periodicity of the forcing, the thermal forcing, as the planet spins under the input of the star, and the natural or free oscillation frequency of Earth's atmosphere. And it turns out that for the Earth, with its modern atmospheric composition, that resonant state should happen at around 21 hours day length. And at that point, you'll get an exaggerated, a strongly exaggerated atmospheric tide, thermal tide. Now, Kelvin thought that the Earth was in a resonant state. And so he speculated that this was actually acting on the spin evolution of the planet and the day length evolution of the planet. By the 1950s, meteorological data had gotten much, much better, and it was clear that we weren't seeing the kind of pressure changes and density changes that would suggest a resonant state between the forcing frequency of thermal input and the natural oscillation frequency of the atmosphere. So it's not happening for the Earth, but it could have happened in the past. In fact, there's been work done to suggest that this may have been the case a few 100 million years ago when the Earth's day length was close to 21 hours. So it's very, very interesting. Yeah, this isn't too important for what I'm about to say, but to first order, that resonance day length, it scales as the square root of m over t. M is the mean molecular weight of gas. In the atmosphere, T is the temperature, so there is dependency on the composition of the atmosphere, dependency on the temperature itself at any given moment, what that resonance day length corresponds to. So to skip a whole bunch of technical work on this, something very interesting can happen in principle. And that is when that torque, that resonant thermal torque, if you're in resonance at a particular day length for the planet, and you have the right configuration around the parent star so that the torques exerted on the planet because of the thermal tide can be similar in magnitude to those of the regular stellar tide, it is possible in principle to have a situation where the two things can balance, where the stellar tide trying to slow down the spin of the planet, the thermal tide trying to speed up the spin of the planet can cancel out, can balance out. In fact, it's been proposed that back when the Earth was at around 21-hour day length, this may have happened, except there it was the lunar tide was the thing that was being balanced out primarily. As a result, if you have a balancing out, it means that the spin evolution of the planet will stop. It will be stalled. Okay, and it may be stalled for quite a long time unless something changes. So, for example, a dramatic change in planetary temperature or atmospheric composition could break you out of that resonant state, break you out of this stalled balance between the thermal tidal torque and the stellar tide. Again, without going into all of the details, if I thought I could be more efficient in this talk, I would have a whole bunch more slides. I looked at this a couple of years ago and looked at the possibility for exoplanets. And it turns out that for exoplanets around stars that are maybe a third to half of the mass of our sun, given their potential orbital habitable zones, and therefore the kind of spin down due to stellar tides that we might expect, there's a possibility, there are many parameters here and quite broad unknown constraints on things, but there's a possibility of precisely this sort of stalling to happen. So in other words, when and if we start to measure planetary spin, we shouldn't be too surprised if we find systems where we look at their age and are confused by the fact that the planet is still spinning quite fast, rather than having slowed down as we might expect. It could be that it's gone through one of these resonant trapping conditions, had its spin sort of stalled, it's had its spin down stalled. Okay, so last few minutes, what does this have to do with life? I proposed that I could make an argument for how life could impact planetary spin. How is that going to work? Well, it's going to work off of this. Okay, here's a mechanism to interrupt the expected spin evolution of a planet. Okay, so how can life play a role in this? Well, I said that atmospheric composition and temperature influence the resonance day length. So there's an interesting observation to make about oxygen in particular. So the resonance period turned out to actually be affected quite strongly by things like the rise of ozone in a planet. If you start to put ozone into a planetary stratosphere, the ozone results in significant heating of the stratosphere, and that winds up shortening the resonance day length, the resonance period. So instead of being 21 hours, it'll shift it to maybe 19 hours or something like that, or even less, if you build up ozone in the planetary stratosphere. Similarly, if you have molecular oxygen in a planetary atmosphere, that will tend to actually lengthen the resonance day length, and that's to do with variations that imposes in the scale height of the atmosphere, if the atmosphere is very much like the Earth. So a lot of this is focused on a very Earth-like atmosphere. It's to do with a nitrogen-dominated atmosphere. You start inserting molecular oxygen, it will impact the scale height of the atmosphere, how much it sits above the planet, and that, of course, impacts the frequency of free oscillation of the atmosphere, and therefore the resonance day length. So a little diagram that just sort of displays all of that in pictures rather than words. So that's interesting. There's an interesting fact about understanding or speculation about what has happened on Earth. So Earth did not start with an oxygen-rich atmosphere, as you know. Oxygen built up over a very long period, starting about 2.5 billion years ago, with the rise of organisms that would inject oxygen into the atmosphere. And it is thought that the first thing to happen would have been a buildup of ozone in the atmosphere, because closer to the surface of the planet, any oxygen that was being produced was being quickly absorbed or quickly reacting with surface minerals. And that soaking up of oxygen would have actually delayed full oxygenation of Earth's atmosphere for a very long time, hundreds of millions of years. And we think that is likely what happened. So on Earth, at least, if you have oxygen-producing organisms, phototrophic oxygen-producing organisms, first thing that happens is ozone builds up. Second thing that will happen much later is you build up molecular oxygen in the atmosphere. Both these things impact that resonance daylength. So is this a way for life to imprint itself on the rotational history of the planet? So, two more slides. So here's just a sketch of how that might play out. So what I've plotted here is day length versus time for a planet. So imagine the planet forms down at the lower left here, and it just undergoes the usual kind of spin down due to stellar tides. So its day length is increasing as time goes by. But on this particular planet, there's life, and at some point, some of that life evolves to generate oxygen, perhaps through the mechanism we're most familiar with, which is photosynthesis, oxygenic photosynthesis. The first thing that will happen is that ozone rises in the concentration rises in the stratosphere, reducing resonance day length. So it could bring the planet into resonance sooner than it would otherwise have gone into resonance. And it could conceivably then stall the evolution of planetary spin. So maybe instead of following the dashed line, this planet would then follow this lower curve for its day length evolution or its spin evolution. So basically just slowly change its day length. As oxygen rises in the atmosphere, that will lengthen the resonance, so it kind of keeps tracking the day length of the planet. So it increases the odds of keeping the planet in that balanced state where its rotational evolution is kind of stalled. Then some point later, something could happen. Maybe there's an ice age or some imbalance in the planetary environment, changes the temperature rapidly, or some new organism comes along, gobbles up all the oxygen or something like that. You could break out of the resonant state, break out of that balance between torques. And then the planet would just resume its normal spin down. This is a possible scenario. So in this case, I would argue that life could indeed imprint itself on the rotational history of a planet. And really just, I'll put this almost last slide up. If you want to be even more outrageous, you might ask, well, it sort of feels like there could be some kind of feedback at play here that actually prolongs the maintenance of a fast rotating planet for the benefit of organisms. So phototrophs that produce oxygen, for example, may prefer faster rotating planets. We've seen from the earlier work that I showed you that a planet with a 16 times rotation period has an optimal amount of surface area that is temperate. But also, if you're a photosynthetic life form, regular flushing with photons is important. Regular supply of photons is important, but as is also downtime from that. Okay, so day-night cycle, having a fast day-night cycle could be a better deal for you in the long run. So the really wild notion, and I don't know exactly how this might work, but just to put it out there, is that perhaps there's some sort of Gaian-like or Gaia-like feedback that could engage. It's not a conscious thing, it's not a cognitive thing, it just happens. That the rise of an organism that modifies the atmosphere in a sense that it can stall the spin down of the planet, maintaining a faster spin, may be better for that life form. And so there could be some kind of feedback that keeps that going for longer than it would otherwise, that keeps that planet spinning faster than it would otherwise, to the benefit, to the selective benefit of those particular life forms and lifestyles. So a little bit crazy. This is my last slide. I think planetary spin is a really interesting thing. It's such a simple property of a planet that we haven't really bothered worrying about it terribly much. We've worried about things like the Earth, or we've thought about tidally locked planets. We haven't really bothered to think about everything in between. We've got this amazing simulation tool. We can now ask some of these questions. I didn't show you further work that we've done talking about things like the carbon silicate cycle, fast and slow spinning planets. It turns out there are impacts of spin on things like the carbon silicate cycle stability. And my argument would be all of this is saying actually, yes, it is worth thinking about ways we can look to constrain the day length of exoplanets. It would provide an enormous amount of additional insight into their surface environments, into their possible history, and so on. So I will stop there. Thank you so much.
Hey, thank you so much, Caleb, for this. Very instigating. I wonder if there are questions coming from the audience. Anyone? Well, people are still thinking. Let me ask one question. How would your conclusion? You mentioned that the models that you looked at had no planetary tilt, right? Because I'm sure that probably complicate the models a lot. But I wonder how much of this would persist, including the resonance effect, if you had some level of planetary tilt in there.
Yeah, it's a good question. So I think the resonance effect is still going to be there. That really is to do with the diurnal forcing. It's the daily forcing of the atmosphere. And certainly for the Earth, with its tilt, I mean, I didn't say this explicitly when Kelvin was working this out and people subsequently looked at this, they absolutely incorporated the tilt of the Earth and the possibility that at different points in the planet's orbit, the forcing varies because of seasonality. I think it's possible you could modify that resonance in a couple of different ways. We know that on the Earth, for example, we have a different land-ocean distribution in the northern hemisphere versus the southern hemisphere. So seasonality will definitely play some role in how that resonance takes place and its impact on the spin rate of the planet and the coupling between the atmosphere and the surface of the planet. There are differences between ocean and land coupling. So there's something more to definitely investigate there. I think the overall outcome, for example, of seeing how planetary temperature, the global mean temperature declines with increasing day length, will probably hold for most sort of moderate axial tilts to a planet. I don't think that will change too dramatically. Where you get the substellar cloud formation, that may be affected a little bit by obliquity, but not too much. But yeah, you're absolutely right. I mean, we did the simplest thing, which was, okay, let's just remove axial tilt because it's a complication. I suspect a modest amount of axial tilt will not change any of this terribly much. There are interesting questions that people are looking at with this same model of extreme axial tilt. So what if the axial tilt is 90 degrees? And some of the interest in that is actually because of places like Mars. So the Rocky 3D climate model, we have a version that will work for Mars. It's complicated because of dust. You actually have to have a whole dust model in there. But Mars, unlike the Earth, has had really dramatic swings in its axial tilt for periods of 10,000 years, 100,000 years, and so on. And that axial tilt has perhaps gone as far as 60 degrees over, which is why we think there's some evidence of glacial regions at lower latitudes on Mars. That introduces, definitely complications for the sorts of arguments I'm making. So it will be interesting to see, how that actually plays out with this. And of course, the spin evolution of the planet will be affected by this to some extent, the axial tilt, although the tendency is for the axial tilt to gradually align itself vertically because of gravitational tidal effects.
Yeah, well, great. We have some other, I have one more question about this, but I'll hold off because we have lots of questions from the audience. We have our exoplanetary scientist, Elizabeth. You have a question and you can talk, so go for it.
Excellent. Yeah, I was wondering in terms of this this modeling playground that you have, what are the kinds of things you're able to change I was especially interested in the kinds of, as someone who loves M-dwarf stars, the kinds of things that you're able to tune to model an M-dwarf planetary system.
Yeah, so it's a good question. So it's, you know, it's much like life in general. It's an endless process of development and growth. Yeah, so we have a capacity, or at least I believe it's now ready to roll, to actually have things like M-dwarf spectral input to the planet. So you know, what happens when you shift, as you know, when you shift to a lower mass star, the spectrum is redder. You have to deal with more of the atmospheric chemistry and radiative processes in the infrared. And so that is quite a task. So yeah, so we can swap out different star types. And back when we did these runs, that wasn't quite ready for prime time. So we just stuck with a solar-like spectrum. So we can absolutely do that. We can, of course, yeah, we can shift orbits. We can modify how the chemistry works in the atmosphere depending on the stellar input and so on. Sorry, there was something else in your question, or was that?
Nope, I think that was just a general interest in these kinds of things.
Okay. Yeah, no, and I should mention as well, we've used this model, we've done ocean worlds. So for example, Proxima Centauri b, some of my colleagues have modeled that using this simulation package as an ocean world. And that's very interesting. You can look at things like ice coverage on an ocean planet if Proxima Centauri b is an ocean world, and ocean salinity and how that changes with circulation patterns and assumptions you make about the atmosphere above the ocean and so on. We're gearing it up, or it actually is geared up now, to do things like geothermal input. So the idea is to move towards not just open ocean worlds, but ice-capped ocean worlds that have geothermal input as well.
Okay, awesome. And Christina, I think I let you talk. Do you want to ask your question?
Sure, thanks.
All right.
Yeah, I'm just curious whether you're looking forward to any particular data from Perseverance that might feed your modeling.
Very timely question.
Mm-hmm.
So yeah, so we haven't, my understanding that those, you know, the many people involved in this project, those working on Mars have looked at paleo Mars. They haven't really done a full modern Mars yet, but the capability is there. Early on, a couple of years ago, the initial Mars model was used because we could compare it to ground truth data for curiosity in terms of things like temperature and seasonality. So it will be interesting to see whether, yeah, Perseverance will obviously give ground truth data for local temperature, pressure, wind, and so on that could be useful. I don't actually know what we would do with that. You know, one of the things, as I mentioned, with Mars is the dust. And it turns out, so any given time, I've forgotten what the exact number is, at any instant, there's like 10,000 dust devils on Mars. And over the course of a Martian day, there's millions of these things. And dust is endlessly being moved around. It's like this most annoying sort of house cleaner you can imagine. You take dust from one place and they put it somewhere else. But that dust, as it's wafted in the atmosphere, obviously modifies the thermal and transmission qualities of the atmosphere. You actually really need to take that into account. And that's one reason modeling Mars is quite difficult. I should say, I mean, other groups have specific Mars models that are utilized for space missions because you need to kind of know what the condition of the atmosphere will be when you enter it, the spacecraft, and so on. But yeah, so we'll see. There may be some application.
All right. I have one last question here from an anonymous attendee, so apologies for not giving you a voice. You could see, as you pointed out, that the landmass got considerably colder than the water bodies on a 256 times slower rotating planet. Why is that? In general, how important is it to take into account the composition and distribution of the surface in addition to the atmosphere in your models?
You go back to that
the picture of the rotating. Yeah.
Yeah. So why is this happening? Well, I think part of it is that the nature of land ice and snow is different than sea ice. And so there's an albedo effect that goes on once land masses start to get cold, and you start to get, in a model like this that has water in the system, has a condensable species like this, the more snow and ice you get on land, it gets more reflective, and so it gets colder and colder. So that's part of what's going on here. The other part is to do with that substellar cloud cap. That, gosh, yeah, obviously it moves across the surface of the planet, but it's sufficiently good at shading the planet that it sort of sets things in motion for ice deposition and snow deposition on the continents. And they don't necessarily thaw out by the time they're back underneath that snow cap in the same way that happens on the oceans in this model. So these oceans are fully flowing oceans, so they have depth to them, and thermal inertia is different in the oceans. Land has much less thermal inertia, so land can chill down quicker. So I think that's a partial answer to that question. There was another piece to the question as well that I'm missing now.
I think we're kind of running out of time. So my suggestion is that those of you who want to join us for the virtual tea, we can continue it over there. That'll be great. So it's 4:09. I would say in a minute, let's all meet there, whoever wants to come. Caleb, thank you so much for your presentation, for your willingness to do this on a Friday afternoon. Snowy New York, snowy here too. And thank you all, and I'll see you soon. Okay, bye. So let's re-meet at the other Zoom link.